Yeah,
because there's a glare and something
on the top.
Yeah. Actually, what is following it, then it is not a problem. You can yeah. No.
It depends on the metric. Blackboard horizon.
So we're very happy that Sameer agreed in the middle of this vacation to come and spend the day with us. So he's here for much of the day. We'll go out afterwards for lunch, so join in. He'll tell us about the Giant Graviton Expansion in AdS5.
Okay, thank you very much. Thanks for the kind invitation. It was very nice. It's always nice to come here. So I hope it's informal. Please interrupt and ask questions and so on. Can people hear me in the Zoom? Yeah, it's all good.
Yes, no problem.
I'll talk about some work with my student, Yorgos Eleftheriou and the postdoc Marti Rosalio. So we wrote a paper last year, and we're also working on another one. It's a mix of both these things. So I'll tell you about the idea of this giant graviton expansion, something which is in the last few years people are working on. I'll just jump into it. So the context is AdS. Think of AdS CFT. I mean, more generally holography. And in order to be concrete, to have one example, I'll take n equal to 4 super Emmys and type to be on AdS5 times S5. Okay, but a lot of the statements I make is much broader. And you can ask me which statement is broad and which is not. So the subject is still developing, so I thought it's good to take something concrete. So think of this Yang-Mills theory, this 4D, put it on some compact manifold, let's say S3. So there's no infrared divergence. So now in this context, you can think of this as some infinite set of couple quantum mechanical variables, and you can calculate a thermal partition function. That's completely well defined, thermal type partition function. Again, to be concrete, I'll discuss a supersymmetric index. At least some of the things I say should hold outside supersymmetry. Okay. So take UN theory, and you consider some supersymmetric or superconformal index of the following type. Superconformal index, which is trace over this S3 Hilbert space. So as I said, today we'll consider indices, and then Q to the R. Q is some external parameter. You can think of Q as some e to the external gauge field, which couples to some charge R. Okay, I'm being slightly schematic. And this is some series in Q, and we usually write it as a Q expansion. Okay, A n Q to the n, where A n are some numbers. That's what interests me. So what is A n? A n. Yeah. So yeah, I'm being a little schematic. So you can do this for all kinds of thermal type traces. You can put you can even put multiple chemical potentials and multiple charges. Yes and no. I mean, that's the most general thing you can do. But you can also, even if you're interested only in, so firstly for thermal, this, if you don't have a minus on the F, you can have e to the minus beta h. That's the bare thermal thing. Even if you're interested in superconformal indices, let's say the most general one, which is 1/16th, you can pick a combination of charges that only gets contributions from 1/16 BPS states. So it's kind of the simplest thing that I'm writing. And it's fairly general is what I'm. All right.
Sorry, could I request the people to use mic in the audience because it's not audible?
Okay, Ashok's question, or I could also repeat the question. This Ashok asked whether it's important to have one chemical potential or multiple chemical potentials. Okay, now what is AN? AN is the number of gauge invariant operators in the theory. Okay, but by number here, of course, I mean the index. Okay, and for the last few years, I've been making a very big deal of the fact in many of my papers that those two are not the same thing. But today, that's not so important. But by number here, I just mean the index. Okay, so number of bosons minus fermion with charge equals. Okay, so it's a microcanonical Hilbert space. And now let's think about the behavior of these coefficients. So firstly, you can do the following. Fix the charge and scale the rank to infinity. Okay. In this case, AN gets contributions. So what are these gauge invariant operators? So in this case, the gauge invariant operators are free multi-traces. Okay. So because the rank is infinite, there are no trace relations at a fixed charge. So it's generated, the gauge invariant operators are something like this. Something of this. Okay. So these I'll call single traces, these are multi-trace. Okay. Good. So that's the boundary interpretation. And then the bulk interpretation is its free multigravitons. Okay. Okay, and this you can think of. I mean, I don't think this should be new to anybody, but let me just review the logic. As n goes to infinity, one way of thinking about it is that each trace is a string. Because n goes to infinity, this is, you can think of it as a free string. And for small charges, the oscillations of a string is just a graviton. That's one intuition you can make. Or you can check this, or some basic AdS that for small, if n is infinity, and you ask what are the states for small charges, they're just fluctuations of the gravitational field. Okay.
Small charge. Otherwise, in a sense, what you really have in mind is like when at large lambda only the light modes. So otherwise, in general, there are stringy modes. So.
The string, yeah, exactly. So that's why the intuition is that for me, the correct intuition is that this should be, each single trace should be thought of as a string.
But they're not necessarily gravitons unless.
So then, for very small charges, I'm thinking of it as graviton. Okay. So once you hit the scale of the winding of the string, then you'll also start to see those things. And then for the things that I want to do, it turns out that it's only the graviton. Yeah. No, so here I'm fixing n and taking n to infinity. There's no upper cutoff, but it's like this should be strictly infinite. Strictly zero. Okay. So indeed, this is a very good question. So suppose you want to put this on a computer. You say the rank is, let's say, 100 or 1000. Until when should we trust this thing? Okay. So this statement is asymptotic. It's only in this limit. However, for the index, in fact, that was the very next point. For the index, you can make this slightly more precise, which is that I'll come to this in 1 second. Okay. Let me say it anyway. For the index, you can make this more precise. For the index, for n equals 1 all the way until n, exactly until n, this interpretation turns out to be correct. So both of you made comments. So the statement is that for superconformal indices of this nature, for charge equals 1 up to n, exactly until n. Now, here I'm simplifying life slightly. Sometimes it's 2n, sometimes it's 3n. That 2 or 3, 1 or 2 or 3 depends on the nature. It depends on whether this starts with q to the 1 or q to the 2. But let's say it starts with q to the 1. I mean, let's say this is 1 to infinity. Okay. Then this statement is true, that the index for the first n values of charges is precisely reproduced by the index of multigravity. Okay, this you can, it's not obvious, so this you can give a proof of this using some representation theory of the various things. Okay. And you can see that at n plus 1, things start to vary. Okay, and that's exactly where we are going. But let me say one more thing right here. That instead of this limit, you can take another limit, which is you can take n to scale as n squared. Okay, this many people here are also interested in. In that case, the interpretation of this in the bulk is that it's the entropy of the black hole with that charge. Okay. This is not what I want to discuss today. Okay, so in the last 5 years or so, there's been a lot of progress on this. So this is old stuff. There's been a lot of progress in the last 5 years to show that that black hole entropies contain when the charges scale very large in these indices. Okay. In fact, last time I visited here, I talked about that. But there's another scale in the problem, which is what I'll focus on, which is n. Okay, so when there's an index, there's no alpha prime, and so the only scale in the problem is just the rank. Okay. So you have to ask, how does the charge scale with respect to the rank? Okay. So if you plot it, you'll see that for very large charges, when it starts scaling with n squared, there's an exponential growth. For small charges, there's this graviton. But there's a third scale, which is n. This is an intermediate scale. And this is the scale of D-branes. D-branes. Because G string says 1 over n, and the mass of the D-brane is n. Okay, the mass of the entropy, the mass of the black hole roughly scales as n squared, because that's 1 over g Newton. So there's an intermediate scale in string theory. Okay. After the talk, you can ask me how does it work in M theory and so on. Okay.
Half BPS, it's like small black holes. Is that
yeah. So when I said black holes here, I should have caveated it. This is when that index contains, when there is a black hole, which preserves the same supersymmetry, same symmetries that the index is calculating. For highly supersymmetric objects, you can either think of this as small black holes, or you can think of it as integrating over supergravity solutions. Many ways to think of it. Okay. Sorry? Yeah, so all of those gravitational configurations appear at this. Okay. Now, so this is the physics at this scale, and as I said, you can sort of make this very precise that at this scale something new happened. Okay, so that's what the giant graviton expansion is about. It says that so it's another way of writing the same index, okay, of getting sort of new numbers out of it, and it's as follows. You write it like this. So first, so the statement is that for the index for n equals this, in is precisely equal to index multigraviton. Okay, that's that statement. So that means that for the first n charges, these two are going to be the same. So I should have said this as well. This fact that for fixed n, as n goes to infinity, in this limit, everything is graviton, this partition function, I can call I infinity of q, which means that for any charge in that, I've already taken the rank to infinity. Okay. Now, there is something new happens at q to the n. I might as well factor out I infinity. I mean, I can or I cannot, but this is the right thing to do. Then it turns out there's a new series here. This is B0 plus B1Q plus dot dot dot. And I'll call this B01, B02, etc. Then similarly, there's a new series at 2n. Thank you. This is always 1, B1, B2, etc. And now it's 2. Okay, so I hope the pattern is clear. We factor out I infinity and then ask what happens starting with n. Maybe I meant n minus 1 here. Yeah.
If you know the exact form
Absolutely,
of the,
absolutely. So that's the next point. Yeah, absolutely. Thank you. Let me just make some points, exactly. So the first, let me write. Just 1 second. Sorry, what was the question?
Thing is in the sense of some general series expansion kind of factoring.
What this factoring?
Yeah, this fact I infinity into Q. I mean, it's not.
They're all Q series. Everything is like this.
Yeah, but both
so if you
of
have
them
two
are,
Q series, you can always multiply it.
You can also multiply it, but you can't all. You can divide it, and in the sense of an infinite series. So you
Yeah,
divide
it all
into
starts.
infinite series.
I infinity starts with 1.
Yeah.
So perfectly well defined. Okay. Yeah, so that's why I wrote this first and then divided by. This equation should be completely clear. Okay. And then you can divide by it. Okay. Now, let me make various comments about this. Even before what Ashok said, there's a question as to, actually, it's a related comment. So mathematically, what does this mean? So I haven't given you a definition of how to do this. Firstly, there's an ambiguity here. That's why I wrote this below this. These B0, B1, B01, B11 up to B2n minus 1, 1 are well defined because I just factored out and they're the first.
Sameer,
Yeah.
so these B0s are all independent of n. I
Okay,
infinity of Q is
let me just make a few comments. I think they will tick all of these points. Okay, they're absolutely the right questions, what you're asking. Okay, firstly, let me make this point. These are, so let's do this experimentally. How do we do this? Given this, you factor out I infinity. Then until here, there are zeros. Then you get some n numbers here, which are well defined. Okay. Then here, there is an ambiguity. Okay. And I'll tell you what the statement means. The statement means that there is some expansion of this type. Okay, let's call it nice. It's a bit aesthetic at this point, and I'll make this more precise. But in order to be, even aesthetically, in order to be well defined, this is Loga's point, these numbers better not grow exponentially with rank. Okay. Otherwise, it's a completely meaningless expansion. But the exponential growth is here. Okay. So the statement is that the B K M, in the simplest case, they're constant as a function of rank. Okay, just like these first numbers were 0. I'll put 0. Okay, so the second is what is called stabilize to at most polynomials in the rank. Okay, so yeah.
so you are allowing them to be independent.
Yeah, so the simplest case, so in the simplest case, or if you refine this as much as possible, they turn out to be constants. If you sort of distinguish all the states, then there will be constants. But then if you're summing over it, there'll be small polynomial dependence.
These polynomials are bounded degree? Like
Yeah, so each, given the index, so you should think of it like this really. So first try to refine this as much as possible, like just distinguish all the operators. Take the free theory, distinguish all the operators. Then if you play with this a little bit, you can convince yourself that they'll all stabilize to constants as the rank grows. Then what you're doing when you don't have the refinement is you're summing over them. But that depends on the theory. Maybe you sum over one charge or two charges. That fixes the degree of the polynomial given the index.
No, so the bk of n, the degree is determined by small n or?
No, it's fixed by the theory and which index.
Yeah, so let's say we are given a theory.
Yeah,
bk of n,
Yeah.
small n.
yeah.
What is the degree of that in
So
capital N?
that depends on the index. So let's say you are one. So for the half BPS index, they're constant. For
Okay.
116, that turns out to be cubic.
For any arbitrary small n.
So this is independent. So I'm saying, think of this way, vertically as a function of the rank.
Okay.
So fix the charges and ask how does it behave as you increase the rank. Is that polynomial that I'm talking about?
Yeah. 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 I think, it's a question of definition.
Yeah. So in fact, it's the opposite. So if I didn't make any statement about this, then it's sort of a meaningless expansion, right? Typically, if, for instance, I can always write any series as like this if I go for exponential growth. Okay? The fact is that all these series, what happens is that these things stabilize. That's the slightly non-trivial part of it.
I'm just trying to understand, like, do you have a rule? If you have a bk of n,
Yeah.
let's say we talk about half BPS and n equal to 4.
Yeah.
Just to be definite. Bk of n, do we know that it could, the highest power of capital N is
Zero.
It's a 0. It's just constant.
Okay, that's constant. For 116, there's 3.
So and that is proven for all k and small n.
Yes. So yeah, let me just make one more point. So if we have an explicit formula for GM, then we can answer all these questions. And in fact, we do. So based on that, you can figure out all these.
Maybe I'm missing some point, but the exponential growth is a question of the radius of convergence of Q, which you want to keep to be Q equal to 1, I guess, right?
Good. Excellent. So this thing that I just mentioned, that these things stabilize, is formally they're called stabilization of power series. So you can think of it, if you want to think of this as a function of Q, like you're doing analytically, that, assuming there are no poles, all these are assumptions that sometimes don't hold, then it's the unit disk. Okay? But what I was trying to spell out is, I was trying to avoid such analytic things. There's a notion of stabilization or convergence in the power series sense. You just do an expansion on a computer and ask, and just do it for n equals 1, 2, 3, rank equal 1, 2, 3, infinite, and ask what happens to these things. And in fact, experimentally, you'll see that these things start to stabilize. Then you have to make a guess here because of this ambiguity and do the same thing. Okay. So in this way, so let me make some. So in this way,
sorry.
Yeah, go on.
Just one question. So sorry, the Q to the n I understood, but now the Q to the n is this thing is
Q to the 2n.
Yeah, the Q to the 2n.
Yeah, that's what I'm saying. So what happens? So the history is like last few years, 5 years maybe, 4 years. Actually, 2 years. So there's been many such expansions. Proposed. Okay. So what I mean is that, so until here is clear. After that, you subtract this, and then you ask what remains. So you guess a formula for this. Okay. And then you subtract that. There's an ambiguity there, where you guess, subtract, and then you'll get that. And similarly, so there's some aesthetics there. So there's some nice formulas which were discovered by, firstly, there's a whole series of works by Imamura and collaborators. And then there was a nice paper by Gayotto and Lee. Okay, they did lots of such experiments. Okay, and all of them involve some kind of, proposals, guesswork, things like that. And you say, okay, look, I find something else. So to Q to the n, Q to the 2n, Q to the 3n, experimentally you can do such things and find nice formulas.
B110 or B,
this one?
B10, yeah, B110.
B11, yeah.
Yeah, but B upper 1, lower 10 is the same as Q to the 2n for n equal to 10, right? I mean.
No, it's that plus that, meaning once you, it's not the same, this is an infinite series. So I'm saying is, you get the, let's say n is 100. So you get the first 100 coefficients. Then you guess what's the analytic form of that.
Okay.
So you extend it. Okay. What is artificial is to stop it. Okay, because the interpretation now, I'll come to that, is that these are fluctuations on top of determinants of D-brane. Okay, so you should not cut it off. Okay. In the past, some people did that. You can do it mathematically, but I think that's the wrong thing to do. How to extend it is ambiguous, and that's exactly the operator mixing problem in the Yang-Mills theorem. Okay, so in this way, many things were discovered. Then, yeah, of course.
For 160 BPS.
Yeah.
I mean, the natural thing would be to fix 4 charges and then extend.
Yeah.
Because who do that? And is it who that these BNs are in capital N?
Exactly. The 4 maps to the 3. The reason you get a cubic is because there are 4 charges and you're summing over them. If you that's what I said earlier. If you refine it as much as possible, then they become constant. Then there's no dependence. They're stabilized completely. So this polynomial growth is just, it's easy to understand. It shouldn't bother you. Okay. So there's some non-trivial thing happening here that it's stable. Okay. Then there's actually an explicit formula. So even formulas, there are multiple formulas for this reason because there's an ambiguity. But for any such index, or in fact for any such series which arises as a unitary matrix integral, there's a completely explicit formula for GM. Okay, a formula, it's not the unique one. So this was various people. So I wrote some formula using free fermions, and then Liu and Rajappa developed it further, and in a very nice paper by Raghu and Raghu, if you're online, can you please? So there's Yiming Chen, Raghu,
And Haifeng Tang.
and one more person.
His name is Haifeng Tang.
Okay. Sorry, I didn't hear it, but it's that person. Okay. So overall, so there's a bunch of work, and by now there's a nice formula. There's a very nice formula with different interpretations. Okay, so all of this, I'm not going in the direction. I just wanted to give you a brief overview of what is known about the formulas themselves. Okay, and at the end of the day, either from these sort of guessed formulas or these explicit formulas, they're all adding up to tell you that these things should be interpreted as, so GM, M, product of M determinant operators plus fluctuations. Okay, that's the boundary. And in the bulk, it's M D-branes, wrapped D-branes, plus fluctuations. Okay, and these wrapped D-branes are precisely what are called giant gravitons. Okay, so notice that from the first n of them, you see that the quantum numbers have to be exactly the same as gravitons. So these are wrapped. So these D-branes don't carry D-brane charge, or monopole charge. They can be dipoles. These are the giant gravitons. So they're wrapped, branes wrapped in cycles in AdS space, AdS times S5, which carry the same quantum numbers as gravitons, but they have mass which grows as n, or charge which grows as n. That's the bulk interpretation. Okay, so these formulas begin to look like that.
No, I was just wondering. There are giants and there are dual giants.
I'll come to all of this. I'll come to this.
They will be
yeah.
both.
So I'm trying to develop it slowly. Yeah.
I had the same question.
Same
The cycle could be anywhere.
Okay.
Right?
Okay.
Yeah.
Okay. So far, I just said. In fact, I didn't even show you these formulas because I don't want to go there. Okay. What they look like is that there is sort of multiple stacks of giants and they're interacting, things like that. It's slightly complicated, but so all this is still in progress. I think it's not fully understood. Okay, any other questions? So one more comment. I said I'll answer some questions later. I hope I did. answer all the questions. Yeah. So one more comment is that, so this whole thing, I think in a very broad framework should be understood in terms of this open, closed, open triality, where the original index as defined in this boundary theory is one of the open string theories. The closed string theory is this, either as black holes or as sum over geometries or small black holes, whatever you have. And this is the new expansion, which should be the second open string theory. Okay, so this is like, these are open string theories on the branes in AdS space. So it's some kind of intermediate thing. Okay, I'll make this more precise now. It's not only open. You can think of this. You see, it's I(n) over I infinity, which has this expansion really. So there's some universal factor, or you can think of that as, yeah, it's whatever you call it. Yeah.
Yeah, I would also say that you're not really seeing the internal degrees of freedom of these branes, right? It's not like these branes can be non-abelian. So you're just seeing the branes as classical solutions in a sense.
No. So
these coefficients will depend on this.
On?
Like if you had three branes on top of each other.
Yeah, it depends on M. No, here, that's why I put this label. I should have put also rank label, but that we finished. But this, it depends on this M label.
I see. So maybe I came late and so I missed the notation. That M is...
M is just this M here, right here. It's the number of giants.
I see.
These numbers depend on which giant.
Okay, thank you.
All right. Okay, any other?
Does not stop also, right? You're seeing it.
So this is a series, each term of which is an infinite series. It's an infinite series, each term of which is an infinite series. They're all formal power series. So it clearly, yeah. So I think in the past, people had recognized something like this, that you have to sum over branes. But it was not obvious that these things should carry on for infinity. And I think people tried to sort of cut this off and so on. I think this is more beautiful. Okay, you'll see why. That's why I stress this convergence of power series a little bit. Okay. All right. Maybe one last philosophical point is that it's important to have rank finite to make sense of any of these things, obviously. This question of what is the quantization of D-branes in the bulk and the fluctuations to reproduce indices has been addressed by Shiraz and collaborators. It was Minwala, Gayotto, Zahiri. It was a nice paper, couple of maybe Subrat was also involved in. No, not that one. Okay. But that's different from this. I think at the heart of it, that they're both correct, but they give different formulas. At the heart of it, that the old one, in some sense, assumes infinite n. Whereas now it's really important to have finite n. Okay, so what I'm going to do is you have an AdS5 times S5 with some large n, but finite units of flux. Okay, and in that there are D-branes. And now the idea is, can we explain these formulas from quantizing the fluctuations of those D-branes? Yeah.
I mean, if you have black holes,
yeah,
you have to add the black hole contribution.
No,
right?
so it's a fantastic question. So let me tell you. So in this paper, I did many things. I started with gravitons and then went all the way. Now, so I had an explicit formula. And as I said, by now, Raghu and friends have really polished this to be a very nice formula. But one can just check what happens to this, and it's an exact formula. So that, again, this goes back to my remark about convergence. This is really an exact formula for any index. So in particular, the asymptotics of this already contains the black holes.
I see. Okay.
And that's why this remark is important. That it's really, you can call it open or open plus closed, but it's different from the usual closed string expansion.
But
Now,
then shouldn't one think of these as black hole microstates from the bulk
good. So that's exactly what I was going to say next. So in some sense, Okay, the 1/16th BPS, as I said, I have a formula. I think
It's half BPS you are saying. Okay.
today I'll do half
I see,
BPS.
okay.
1/16th BPS also have a formula, but it's not yet beautiful enough that I can give a lecture about it. But today I'll do half BPS, but 1/16th BPS, which contains black holes, also this formula is for all indices. Okay, but I'm saying I don't understand it well enough to really discuss it a lot. But what I'm sure of is that there's an explicit formula, and this contains black holes. And what that means is it's an analog. So in flat space, by now we're very happy with this statement that black holes are made up of D-branes. Again, this is the original AdS CFT. What this is saying is that black holes in AdS5 are made up of D-branes in AdS5.
Yeah. But in flat space, at least there are answers, right? I mean, the black hole description is valid in one regime and the D-brane description.
Yeah. So here also so this one, what I'm going to do is I take a background AdS5 times S5. I'm not quantizing the gravitational fluctuations except at quadratic order for this I infinity. So I'm not summing over geometries. That would be this closed string description.
Right.
But it's an intermediate thing. So there's a curvature, and then I'm going to quantize the branes.
Okay.
So it's genuinely different from either of those.
You are thinking of the branes as weakly coupled up.
As weakly coupled up, exactly.
Okay.
And then I'm going to make all this precise because of supersymmetry and localization.
I see, okay.
All of this mix.
Okay.
I mean, you're saying the black hole contribution is already present, right?
Yes,
in the expansion.
Yeah.
But this is slightly different than the usual black hole because this is a wrapped D-branes, right? I mean, if you, how do I say this? Let's say, if they're not wrapped D-branes,
Yes.
they're just stack of D-branes.
In flat space.
In flat space.
Yes.
Then we can think of it
Then
as
you
just
get that.
black hole in the end, right? But this bulk interpretation should be different, right? They should say that the giant gravitons are somehow giving the contribution of black holes.
Exactly. That's exactly what Ashok and my comments said, that black holes in AdS are made up of branes in AdS. That's what I meant. You can just remove, you can forget the first open string theory completely and just keep so that's what this is saying.
As a general statement, for instance, you might wonder if this works for AdS3 times S3 times T4, and then it doesn't seem to work. Right?
Why do you say it doesn't work?
I don't know. Then, these giant gravitons and so on wouldn't contribute to the index.
Why not?
I thought then the index is just protected all the way up to n squared, up to Q1, Q5.
No,
Whereas
so
these things you'd expect would start contributing.
No, I don't necessarily protected.
It's the fact that the gravitons themselves give you the same index as the full index all the way up to Q1, Q5.
Up to the black hole bound. But this, if you want the black hole, you have to go beyond the black hole.
No, I understand. But so are you saying somehow that the giant gravitons in AdS3 will not contribute at Q5, which is where you would naively have thought they would contribute?
So I didn't say that, but so you made the contrary, and I think that's actually incorrect. So so I haven't studied AdS3 very well, but one thing to keep in mind is this formula, well, starting from Rajesh and Fran's work, is a formula due to Eberhard. Remember, what is a giant graviton in AdS3? It's just a string. Okay, so in some frame, it's either a D string or an F string. Like you've studied this as well, right? So there's this formula where you quantize strings, including the long strings, okay, without summing over geometries. Okay? You're aware of this paper. And what you get is the complete partition function. And in my opinion, that should be thought of as this second open string theory or a giant graviton expansion. Yeah. So that's an exact formula. A couple of years ago, Eberhard wrote such a paper.
It's more like a grand canonical.
The grand canonical thing. But that's exactly what this is. This you have to sum over it. Okay, so I think it's all really fitting together well. Okay, so that's any other questions of this nature? You can keep asking, but now I'm going to go to some specific example. Yeah. So I'm going to give the same answer that I gave him. You said and I said exactly the same thing. Black holes so my slogan is black holes in AdS5 are made up of branes in AdS5. If you remove AdS5 and substitute flat space, it's Schrödinger.
So, there's sometimes, like one would want to kind of go to a grand canonical ensemble in capital N.
That's what this is. In capital N, sorry. Yes.
So
Good.
sometimes these,
Good.
these indices,
Yes,
sometimes you want to calculate it that way. is there, is that a better way of thinking about the
Okay, that's a
stabilization?
beautiful question. I don't want to say anything about it, but I believe that that's at least mathematically, that's the right thing to do. I mean, some whatever notion of.
Yeah, in AdS3, that's what Eberhard
That's what
does.
Eberhard
Yeah,
did,
this is quite,
And
motivated my question that
if you look at these indices and some give another chemical potential for the rank, something very beautiful starts to happen, but it's not, I don't know the physics of it yet, so I don't want to talk about it.
Yeah, though, I mean, in AdS3, there was a physics reason, I think, why you needed to sum over n.
I'm not, yeah, I agree with that.
Because of the boundary conditions.
Yeah, I don't know how particular that is to AdS3.
I think it, yeah.
I think there's this dilaton which is being fixed and which becomes massive and so on.
Yeah.
Okay, as I said, I don't want to say things because if I say something, it's going to be wrong. But I can be vague and say it's beautiful. So, okay. All right. I mean, in fact, I'm going to quote Don Zagier, who says that if you have a sequence of anything, the right thing to do is to make a generating function. So, and then study the symmetries of that. Okay. All right. So now I'm going to move to something particular. So I'm going to take the half BPS index in n equal to 4 super n. Okay. So let's just remind ourselves. So this is work with Giorgos Eleftheriou, my student, and Marti Rosalio. So first, let me remind you of what the index is. Okay, so I'm going to put a half, but soon I'm going to remove it because this is the only thing I'm going to discuss. Okay, so this is defined as such. So it's a trace over the half BPS Hilbert space minus 1 to the f q to the r, where r is a certain u1 inside the SO6 R symmetry. Okay, so if you take the complex scalars of n equal to 4 super n minus x, y, z, and ask what is R and the Hamiltonian scaling dimension, I'm going to pick one where this is 1. And everybody else is also 0. Okay, and Hamiltonian as well. Okay, I hope everybody understands what I'm saying. Okay, so this index is the one which saturates this inequality. Okay? Q square is h minus r. Okay, as you can see from this table, this is not 0, it's not 0. So this is the only letter in the free theory that contributes to it. And so it's an easy problem. You just take, I should have said, I'm doing UN theory. It's usually nicer in these examples, so you keep this one as well. Okay. So up till trace z to the n, and then it's only one matrix. So the n plus 1th matrix, this is related as polynomial by the Cayley-Hamilton theorem of the first 10 matrices. Okay, so this terminates here. So this is just equal to 1 over okay. So it's freely generated. So this is the only relation. So I remove it. So it's freely generated by the first 10.
There's a relation which relates z to the power n to the lesser ones. Right?
Sorry, I always get confused whether it's n or n plus. Z to the power n is there, but that involves 1. So I think if you want to ask what is the, so let's see, the characteristic equation is of degree n, like you just said. I think that means that if you want to write this as a function of the other traces, then you need one more power of the matrix. And let's figure it out later.
I didn't understand. Z to the power n is a linear combination of all the lower powers, including identity, right? That's the Cayley-Hamilton theorem.
Yeah, but now you want to ask so let's say you have Pn.
No, you can just do a 1 by 1 matrix, then, the second one will be.
Huh?
If it's just a 1 by 1 matrix, then trace of Z is independent.
Yeah, you can do that. Or what
Has
I'm
to
saying
be
is that what you want is that the it's trace of, sorry, it's x to be, you're right that this is true.
Yeah. So this is 0.
This is equal to 0.
So I can write x to the power n in terms of
give
lower.
me 1 second. So yeah, so the question is, what are these? Right? These are, you want to be, these are not fixed polynomials. They also depend on the traces and determinants. So that's why you need one more if you want to write the whole thing in terms of traces.
Oh.
Yeah, is that clear? The coefficients, right? See what I'm saying? The coefficients themselves, you want to express, you want to write the whole thing with fixed coefficients in terms of these. So that's why you need one more. Okay. I mean, the last one, for instance, is the determinant, no? Somewhere, this is the determinant. We want to.
The determinant to, or you want to write everything in terms of
Sorry, again?
You want to eventually want to write determinants, right?
I'll come to that in a second, yeah. But I'm saying here, first I'm just deriving it from the boundary point of view. Okay, so that's. Okay, any other questions? What is the keep going, okay. Okay, now here comes the formula. So here's the formula. Okay. Is that visible? It's not erasing well, but again. Yeah, is that visible? Yeah. Okay. This is a formula which goes back at least 100 years. You can. I don't want to spend time proving it, but if anybody wants me to prove it, I'll do it later. It takes 5 minutes, but I don't want to take 5 minutes now. If you want to do it, okay, maybe I'll give a hint. You can do this by induction. There's a formula for, never mind. It's probably known to Euler or something. I don't know who, but it's fairly elementary. Okay. And it's clear that whoever wrote it first knew about this giant graviton expansion. Okay, this what I'm saying is it's of the form, exactly of the form that you want.
Sameer, I can't read what you have written.
Okay, let me read
Sorry.
it out, and after this I will try to. Who is that on the?
Suresh from Chennai.
Oh, hi. So IN of half, that's the half BPS index which I defined on the other side, equals 1 over Q Pochhammer infinity, sum m equals 0 to infinity, minus 1 to the m, Q to the m times m plus 1 by 2 over Q Pochhammer m, Q to the m times n.
Thank you. Perfect. Perfect.
How can I solve this problem? Write harder or?
No, there's some light coming out there. So that's just the top line. That's all.
Is that clear now? Okay. Now, one interesting thing is this Q Pochhammer is this, just product I equal 1 to n, 1 minus Q to the I. Okay. One interesting thing which you can almost work out in your head is that this, sorry, before saying that, I'm going to say something else. So why did I say this looks like the giant graviton expansion? This is clearly I infinity. Okay. That's the sum over giants. That's mn, which we want. And this should be thought of as the fluctuation determinant of one giant. Now, this, you can notice, is actually 1 over Q inverse m. Okay, some formal observation. This was made by Mamura, Gayatoli, all these people. For whatever it's worth, but actually we'll clarify this a little more as we go along. Actually, there's a nice story. So in the first paper, we didn't discuss this, but in what's coming up, we'll also tell you what's that. Okay. So you can speculate that the fluctuations on the curved branes look like the fluctuation. I mean, not speculate, it's a fact. The fluctuation determinant on the curved branes are like the fluctuation determinant on the flat branes, except the Q is replaced by Q inverse. That's not an explanation, it's an observation. All right, but I think you should really take this seriously because that's the Q series which we want. You want a convergent Q series in the positive direction. Okay. Okay, so now for the bulk derivation. So think of this as a, firstly on the boundary, you can write a trace or a path integral. So let's convert to path integral because then we want to translate to the bulk. Okay, bulk, you don't have a trace, good trace interpretation. So this you can write as in the usual way as a path integral on AdS on S3 times S1. And the bulk, so what we said is that try to write this literally. So literally, what is it? You first ask in this regime that I said there's AdS5 times 5, you ask what are all the half BPS objects? There are gravitons and D-branes. So, oops, you integrate. Oh, so firstly, there's a number of branes. This is schematic, and then I'll make it more precise. Number of branes, 0 to infinity. Then there's an integration over the moduli space of branes, okay, of giants. Then there's an integration over the fields. So this is brane open string fields plus the graviton field. Okay. And then there's some brane plus gravity, but including all fluctuation of gravity and branes, right? Before I make this precise, you should do this. I'm responding to a question Ashok asked earlier. Although you're in this regime, you should start by self-quantizing all fluctuation. Okay, and this is a function of all the fields, and it could be a function of the moduli, and you should also have this background potential that I said, which is Q. Q is the exponential of this holonomy. Okay, this is schematic, but I wanted a starting point to then try to make it more precise and then evaluate.
In some regime, but these don't really interact much, right?
Yeah, so that's the thing. So it's so far it's all ambiguous because this regime that I described to you is only well defined for kind of weak coupling or small charges and so on. I'm trying to extrapolate this. So I'll do that using localization. That's what allows me to do this. So start by thinking of physics, which is some weakly coupled, weakly curved branes, weakly coupled to the background and small fluctuations, and then we'll take it forward. That's exactly why I wrote this. But I'm saying you can't take this very seriously because, you know, why should this be weakly coupled and why not nonlinear couplings? All right. So this is the moduli space of M giants. In AdS5 times S5 with n units of flux. Okay. All right. So let me describe this moduli space a little bit. Let me describe moduli space of one giant. So ds square is d square AdS5 plus d square S5. With the AdS5 I write like this, minus okay, there's R, T, and a 3-sphere. And then S5 also I write like that. This is another 3-sphere. These two are not the same. Okay. And So gravitons are of course known, but the D3 half BPS D3 branes are also known. These are the so-called giant gravitons. They all spin around this S5 at the speed of light. So I'm taking the half BPS such that there's a U1 charge here. That U1 R is minus I dd5. I'm taking that particular angle. So they all spin around that with the speed of light. So this f phi dot is 1. And then as multiple, both of, I don't know, some people said here, there are two branches. One is giants. So these wrap the S3 in S5, and they are at a fixed point on this 5 sphere theta naught, theta angle, and R is 0. So they're sitting at the center of AdS5, and they've puffed up inside the S5. And then the dual giant, which wrap an S3 in AdS5. So R, some R naught, okay? These are the two branches.
The original path integral is over.
It's this. So I'm a bit.
So it's open and closed strings.
It's open and closed strings. Okay, around AdS5.
So you have to be able to create those giants and dual giants out of some ordinary path.
No, so I'm not doing a full. That will be full closed string. That will be the closed regime. So here I'm in the second open string regime where I'm assuming background AdS5 and heavy D-branes, which, okay, so that's a comment I wanted to make here. So the philosophy I want to take is that this is like, let's say a gas of solitons or instantons, and I want to quantize it. So the original supergravity is like the original quantum field theory. The solitons are, let me say solitons, are the branes. And when I quantize it, there are the fluctuations of the original quanta, those are the gravitons, and the fluctuation of the collective coordinates. And that's this.
But you also have to sum over soliton number.
That's this.
Yeah. So that's part of your original definition of path integral.
Yes,
that right?
that's why I gave this to myself as some starting point, which is halfway well defined. It's not completely well defined because neither of these is explicit. How do you know whether it's one giant or two giant if you're allowing nonlinear couplings of gravity, because it can create a giant? That's exactly what Subrat was also asking. So I admit it's vague, and we'll start here. For small fluctuations, this is well defined. And as often happens in localization, that small fluctuation analysis becomes exact.
Yeah. And then the graviton you have to add separately.
No, it's also here. So right now it's all here. In one step, I'll remove that.
Okay.
Right now it's all there.
Okay.
Okay. So now you look at the spectrum of fluctuations. Okay. This was analyzed in a nice paper by Das, Siewicki, and Mathur. Okay. And the result is that, so in that paper, you'll find the statement that the spectrum of fluctuations is gapped around any of these. But there's actually a small caveat to that. That's why we had to revisit that. It's consistent with their equations, but they didn't pay too much attention. Which is that exactly at, so if you take a giant, now I'm being specific, and I say giant versus dual giant. Okay, if you take a giant at theta naught equals pi by 2, so this is the so-called maximal giant. It's maximal because, so I should have said that, this, you can see it from here. The size of the giants is sine square theta naught. So at theta equals 0, they're basically gravitons, and they grow, and theta equal to pi by 2, they're the biggest possible. Okay, there's a maximum. There's a maximum. That's important. This was the original paper of McGreevy, Tumbas, and Susskind. Okay, that there's a cutoff. Yeah? This is the stringy exclusion principle. There are various names to that. Yeah? As a parenthesis, there seems to be no cutoff on the size on AdS5. I don't want to discuss this, but there's a nice paper by Nemani, and maybe Gautam is in that or not, I don't know, that group, which analyzes that, and effectively you have to take into account dynamics and the way functions are effectively compact. So both of them have some effective maximum size, okay, which is n. Good. Let me get back here. Yeah, so there is a subtlety to this statement of this paper at the maximum point, where there's actually a gapless mode. Okay, and that's very important because now we need to quantize this. Right. So the approach I will take is, I'll tell you in a second. I'll draw a picture and I'll give you the Lagrangian, everything, because that's the focus of my story now. So what is this? So this is a two sphere, theta and phi. This is theta, and this is phi. And on this, these giants are points. Okay. So typically they'll be going around like that. The maximal giant lives here. This picture deceives you. It looks like it's not rotating if it sits here, but you have to be careful because there's field angular momentum. There's a dBi plus Chern-Simons term. So actually this has angular momentum equal to n. The angular momentum increases. Meaning the gauge invariant angular momentum is actually n. But this mechanical thing, it looks like it's sitting here at the fixed point. The zero mode that I'm talking, this gapless mode that I'm talking about, is the one that makes it slip off that point. So there's a tangent plane, and there are fluctuations in that tangent plane. Okay, it's two-dimensional. I said there's actually one gapless mode, but let me go on. So the approach I want to take is,
or only what we can.
So at the moment, it's an approximate zero mode because all these, I've used kind of larger and weakly coupling, all these things that you and Subrat were talking about. But in a moment, it's going to become exact when it's going to be localized. So the approach is you use localization. So Q square is minus R. And it turns out that the fixed points of Q or Q square are exactly the maximal giants. Okay? And you can have an arbitrary number of maximal giants, M. Okay? So this I have explained. Is a colored chalk? Yeah. So this I have explained. So these are the number of maximal giants. Okay. Now, localization tells you that you should go to the fixed points, and it's a one loop exact formula. Okay, so the next story will be that the rest of it is a one loop determinant. I'll also remove the easy pieces first. So firstly, remember that if it's one loop, meaning quadratic fluctuations, then in this brane plus gravity, this becomes S open string plus S grav, and both to second order. They decouple. Okay. And this part just decouples. It's integral over part of these moduli, I mean, these fluctuations, not moduli, these fields, are just the, let me call it H mu nu. Okay. And that gives exactly I infinity. Okay, with the index, of course. I should have said, I mean, I'm assuming all that. There's a S3 times S1, oops, and fermions have periodic boundary conditions, and there's a coupling to R. Okay. So that also explains this. This is a mic, yeah.
So, sorry. So if you have this solitons,
yeah,
gravitons,
yeah,
then you do fluctuations around them.
Yes.
So that's a fluctuation around the soliton solution.
Yes, yes.
Then what is the second thing you are writing?
What second thing?
This
here?
The quadratic
This?
Yes.
So before, so think of the whole gravity plus brane as quantum field theory plus solitons.
Yes.
So when you do the full path integral of the theory,
Yes.
you have to sum over all sectors, all number of solitons.
Yes.
But you're allowing fluctuations of the original theory as well as the collective coordinates.
Okay.
The original theory are the closed string fluctuations,
Yes.
gravitons, and the collective coordinates
Okay.
are the.
I understand.
What I'm saying is that once you localize it, you don't have to worry about things like summing over geometries. That problem goes away because everything reduced to quadratic fluctuation. So all you're doing is some perturbative graviton fluctuation, which just gives this simple factor out there. So you're really summing over giants, maximal giants. Okay, that also ticks one of the questions you asked. How like you don't have to worry about black holes or other geometries.
Yeah,
So,
the presence of this background Riemann flux doesn't have any.
It's very important. I skipped all of that, but here is very important that I'll write the action in a second. Well, not the full, but here so S. In fact, that's the next thing I was going to say. So that's the graviton part. Now you want to do that's exactly the next point.
No,
So,
I was thinking of this formula you've written down of quadratic plus quadratic.
Yeah.
Like there are no like terms which couple the two at the quadratic.
No, because it's a saddle point, right? It's a saddle point. All fluctuations are quadratic.
No, like aren't there quadratic terms which say like a brane fluctuation coupling to a graviton fluctuation?
No, because it's you'll see because it's kind of maximal. Yeah.
Yeah. Okay.
You have diagonalized.
Yeah.
So when you say only, so you're saying in the localization approach, only the maximal giants contribute, but in secretly they have the contribution of all the other
everything. So without localization, if you use large N and say I'm going to include the Q to the R term, and then ask what solve that equation of motion, they'll also tell you that I should go to a sector where there's only maximal charge because I'm putting a linear term in. Right? That'll also take you to some kind of maximal giant, but then it's not clear why the fluctuation analysis doesn't sample the other branes. So if you try to do the exact problem, otherwise it's not clear why.
But secretly they are in a sense there.
It's all there. It's local. So you can think of the before localization. This includes everything. Okay, just that these are the fixed points. Which
but maybe they don't contribute to the index.
That's exactly what the localization tells you. That the fixed points are the only
ones
maximum.
that are really.
Well, one day, no localization, they will contribute to the index. It's just that this is another way of representing it.
That's another way of. There is no. These statements don't have meaning. No, it's only the final answer that's. Okay. Now, this part is also easy. That's just the R charge, the classical R charge of M giants. Okay. So what we are left with is so what remains is this -1 to the m times m plus 1 by 2. You want to explain this as the one loop fluctuation, quadratic fluctuation determinant index of M maximal giants. Okay. I was hoping to spend of the localizing term. I'm going to say that in a second. Right. Okay. The thing that keeps it there. Now, so I was hoping to spend half the talk on this because it's very interesting, but I'll try to speed up. I'll tell you the right things. And I find this story, the following story, very beautiful. It's especially the old timers should, I think, appreciate it a bit. Let's go to m equal to 1. So first, let me just analyze the fluctuations before adding the localizing term. Okay, so the fluctuation m equal to 1 is just minus q over 1 minus. Okay. Sorry, Loga, did you have a question? Yeah. Okay, so I want to show that this is equal to Z1 loop of m equals 1. Okay, the index of that. Okay, so first let me analyze the fluctuations of one giant. Huh? Say again?
The zero mode. Zero mode.
That's this. So the Z1 loop is the integral over all fluctuations of the giant.
Yeah, but I'm just saying that in this sum, in this minus q over 1 minus q, is that a sign of that zero mode? Or?
You'll see in a second. So this is the boundary answer.
I see, okay.
This I'm just
okay,
I'm
you have to get it from integral.
I'm trying to see what needs to be explained. This we've explained, this we explained, this we explained. What remains is this. Okay. So I'm saying I will show. Okay, I'm going to show this now. Let me build it up. So first, let me analyze the fluctuations. Now the fluctuations, first let's do bosonic. Now, let me call rho is pi by 2 minus theta, and this other phi, where phi is dot, is 1 minus phi dot. Okay, so what you're doing, you're kind of chasing the giant. It's going at a speed of light. You're chasing it, and it's at the top. So you're allowing it to slip, and it's this two-dimensional tangent plane that I'm seeing, and I'm seeing it from inside. That's why the minus. Okay, so let me draw that plane like that. So that's rho, and that's phi. This var phi. You can call x1, x2 the Cartesian coordinate. This is the tangent plane to the North Pole. So now if you write S dBi plus S Chern-Simons and take the quadratic term, you get something very nice. So S equals this. L, the Lagrangian, is n times half x1 dot square. Okay. So it's just a particle in a B field. Okay. There have been observations about the appearance of the Landau problem in giants, but not this one. This is yet another appearance which hasn't been noticed. The earlier ones was about the Landau levels being mapped to the sort of non-maximal giants. Okay, this is a new, it's the same Landau problem. It appears in a new way. Okay. So it's a particle in a B field. And now remember that, so this is mass 1, so mass n, and this is q times b, that's also n. And remember the Landau problem that the orbits only, the eigenvalues only depend on the cyclotron frequencies, m divided by qb. Only the ratio matters, so I can just scale this out, okay, as far as the fluctuation analysis is concerned. So the n sits in the classical analysis, but the one loop quadratic fluctuation doesn't have fluctuations of order 1 exactly as we want. Okay. Now, recall the quantization of this. I'll just write the answer. I think most of you know it. So there is, it's a, okay, if there's any student here and you haven't learned this, please do it. It's very, very beautiful. Okay, there's 4 phase space. So I'm going to do it. You can either do it in Hamiltonian or path integral. Most people do it in Hamiltonian because it's slightly more instructive, and I also use that. In the paper, we do both. There are 4 phase space variables, and the P1, P2 are not canonically conjugate to x1, x2. You have to do some rearrangement. And you get 2 harmonic oscillators, A dagger and B dagger. Okay. And now, this is still visible. No? Let me just write here. I'll write in blue. So H, the Hamiltonian, the yellow. The Hamiltonian is, so once I scale this out, notice what happens. From here, you see that the gauge field A1 is minus x2 and A2 is plus x1. So B is 2 in these units. So the Hamiltonian is B times A dagger A plus half. Okay. So the B oscillator is the zero mode that we're looking for. Okay. The reason we kept the two-dimensional plane is this, because the symmetries of the problem is two-dimensional, not one-dimensional. Okay, so you need to keep that. And L, the angular momentum, is minus A dagger A plus B dagger B.
Isn't there a supersymmetric?
So far I'm doing bosonic.
But that half, I was wondering, shouldn't there have been as?
It'll come to that. So this is the bosonic, and in the supersymmetric version, this goes away. That's exactly where I'm going to. Okay, so this is B times n plus half. And this is, sorry, if you're telling me to hurry up, I'll do that, minus n plus L. Okay, so I'm just reminding people of so there's Landau levels n, and each Landau level, the angular momentum goes from -n to infinity. All right. So now it's the new stuff. So now we want to include fermions. This has also been analyzed in the literature for various reasons. Oh, I didn't want to erase that. But one point I want to make before doing that. Notice that there's a Z2 symmetry in the problem. Imagine this B, call this B equals B by 2, call this B by 2, which is equal to 1. There's a Z2 symmetry in the problem. There's a plane and a constant magnetic field. And classically, you can even see this classically. If there's a constant magnetic field this way, charged particle is going to pick a direction. But you can flip the sign of B, and then they're going to go in the opposite direction. Okay, so there's a Z2 symmetry, which is B goes to minus B, and this L goes to minus L. Okay, only for the lowest Landau level. This Z2 symmetry exists only for the lowest Landau. Okay, that's important because the higher Landau level break the translational limits. That's what we'll need because very soon we're going to the ground state. So now we look at fluctuations of boson plus fermions. Okay, good. So now you have X1, X2, and 2 fermions, lambda 1, lambda 2. This gave me A dagger, DB dagger, and this will give me a fermionic CC dagger. Okay. And the Hamiltonian now, this is what you're asking, is B times A dagger A plus half plus B times C dagger A minus half. So the ground states indeed will have 0 energy. But now I want to stress one thing, that let me allow for both signs of B. This bosonic energy level does not depend on the sign. It depends on the magnitude of B. But the fermionic, the spin couples to the projection of B. It wants to align with B. So this is not absolute value. The sign of B is important. Similarly, L is the sign of B because it flips. And now it's minus A dagger A plus B dagger B. And now without the sign of B, C dagger C. Okay. And now I'm going to say something nice, which is that if you just calculate with this trace, I should have said something that the R of my original problem is minus L because of some minus sign I introduced somewhere. I think change some variables here, this minus sign. So trace minus 1 to the F to the R on this super Landau Hilbert space is this. It's 1 over 1 minus Q inverse. There's 1 plus Q inverse if B is positive, and it's minus Q over 1 minus Q inverse. So that's minus Q plus Q square if B is negative. Okay. This one is like the original bosonic problem, and here C dagger C 0. There's no fermions excited, but here C dagger C is 1. One of the fermions has become excited to see. You can see this from these two formulas. I gave you all the formulas. Very simple now. Okay. And that explains the minus sign. Okay, there's a minus sign because one of the fermions is excited, and that also gives you. The bosonic guy had Q to the half. Here, the fermionic guy made it Q to the half plus times Q to the minus half, whereas here it's adding. Okay. So now, many comments to make. So firstly, 1 minus Q inverse. Oh, sorry, this should be Q. Thank you. Okay, Ashok might leave, so I'm going to make one comment, which is that actually this is precisely wall crossing. It's exactly wall crossing, and it's more than what I thought at first. In fact, this is the wall crossing at the heart of all wall crossing problems that we know. What it is an electron in a magnetic monopole, which is what governs the wall crossing in all exactly solvable wall crossing, including supersymmetric black holes. At the heart of the day, this is what this is. Okay, and you can do this by looking at the wave functions. Psi is, so there are two components because of the spinner. So one of them is minus B times absolute value of Z square is holomorphic. The other one is anti-holomorphic plus Z square. So this is the one that's picked. If B is positive, that's holomorphic, it goes one way. And this is the one which is picked. If B is negative, it's anti-holomorphic, so it's going the other way. Okay, and the wall crossing is, so, okay, so this is the physical, so far it's still I'm just analyzing the fluctuations. But now it's clear what to do. This problem is supersymmetric for both values of B. The physical fluctuations are this one. It reduces the R charge because there was a maximum, the giant was maximum. Okay? But the QV deformation we should add should be consistent with convergence of the Q series. That should be the second one. And I'm allowed to add it because QV I can add whatever I want. So I add this one, and that's why I get a minus sign, and I get fluctuations which go above. And there's this beautiful wall crossing between the two things. Okay, so I won't write that down. So this is how the QV action is exactly. So the QV action is very closely related to the physical fluctuation action with a flip of sign. Yeah.
I didn't understand. In your physical problem, you had B is equal to +2.
Yes, right? Yes.
And
that makes sense because the angular momentum reduces from the maximum.
Correct.
Yeah.
But then, so where is the B, the negative B?
Yeah, I'm turning on a QV deformation. So the QV deformation, I can add whatever I want. They're both supersymmetric.
Right.
But I want to add it in such a way that the final Q series is converged. This is just a fluctuation.
Yes.
For the fluctuation, I can use either this or this. But if I'm going to add Q to the n and then sum over Q to the 2n, etc., I want it to be a power series in Q, not in Q inverse.
Okay.
So I pick this. I add that QV action.
I see.
Okay.
But somehow even without this, adding this, the full partition function should give exactly the same answer.
It knows about it secretly because of this, but with some magic which we don't understand. But now we explained it. It knows about it in this, and this was the original observation of Imamura and Gayoto and Lee. That, well, not quite. Then there was a paper by Lee and so on. But that if you just look at the fluctuations of the physical problem, it sums up to this, then you have to analytically continue. And you don't know what that means. And I'm saying that analytic continuation is exactly what we've learned in many other problems. It's precisely wall crossing of this. So this becomes normalizable or this becomes normalizable. So that's, and then we can do this also in the path integral formulation using equivariant localization. You just add that QV. I want to say a few more things, but this is a good place to pause. Maybe 5 more minutes. I want to say something, but so path integral, I won't do it here. You have to do it. You have to add this QV. It's the technology of equivariant localization. And then maybe I want to make 2 more comments. One is that now for M giants, you have a matrix Landau problem. Right? Because now they're all stacked on top of each other. It's the opposite of the dilute gas, but localization allows you to do that. So it's a matrix in the B field. Now there's a small subtlety, which is that this is matrix Z. You can similarly fermions. But now you have to diagonalize it if you want diagonal values. But the Z and Z bar, you can't diagonalize 2 matrices simultaneously. But again, in the lowest Landau level, if you're only interested in the index, they're all holomorphic or anti-holomorphic. So you have to actually diagonalize only 1 matrix. That you can do. So diagonalize Z. And this is well known, there's a van der Waals. And so there are effective Fermi levels. This Fermi has nothing to do with the fermion, the C fermion. What it gives you is that the eigenvalues under L is 1, 2, all the way up to M. And so the Z1 loop is minus Q over 1 minus Q, minus Q square over, and they're all non-interacting because it's the usual matrix diagonalizations. And this is precisely the GM that we wanted. That is minus 1 to the M, etc.
Okay. So the Lagrangian so you're saying the Lagrangian in general would have depended on Z and Z bar?
Yeah, but on the lowest Landau levels, it's only the wave functions are holomorphic.
Yes.
So you can diagonalize.
So, okay. And the fact that it's in the lowest Landau level is because the B is still 2 or whatever.
No, the lowest Landau level is because you only want the ground states. Everything else is paired.
Okay.
So I should have said something. So far, I said, let's just analyze the fluctuation. I only took 2 bosonic and 2 fermionic. There's an infinite number of fluctuations. There's a nice paper by Gautason and Van Maude, who show that they analyze the full fluctuations. And what we showed is that everything else paired up. Even within these 4 variables, there's pairing. And that pairing collapses you onto the lowest Landau.
Lowest.
Okay. So N is 0, but it's L that is. That was the last statement. Maybe I'll stop. I wanted to make one more. I mean, I can say it. So you can also repeat this for orthogonal and symplectic gauge groups. And so there's an index which is known. And the bulk duals are also known. These are orientifolds of AdS5 times S5. So you get AdS5 times RP5. And it turns out that depending on whether you have SO, so whether you have an SP gauge group or SO odd or SO even, the details of the boundary index are different. And that is precisely mirrored in the bulk because, so firstly, one thing that happens is that the orientifold projection, you have to always consider 2 giants at a time and then projects onto the, so you have to identify them. And that removes all the odd angular momentum. You're only left with the projection to even angular momentum. But for SO even, there's actually a new term in the giant graviton, the boundary index. And that's explained in the bulk. So if you look at Witten's paper on baryons and branes, the bulk orientifold duals are distinguished for these cases, or the SO even, SO odd, or SP, by a very subtle thing called discrete torsion. That's like, because there's an RP5, there is a Z2 discrete torsion of BNS, NS, and BRR. And only in one case, both the discrete torsions are 0. That's the SO even case. In that case, you're allowed to have, so the third homology of RP5 is Z2, over the integers is Z2. That means that there is a new possible brane. This is what Witten identified as the Pfaffian of the boundary theory. That brane gives you, that brane is also allowed, but it's rigid in the sense that it's only defined at that point, it can't fluctuate. And that precisely mirrors what you see in the boundary geometry. I won't tell you details. Okay, I'll stop here. Thanks.
Thanks very much, Sameer. Questions? Firstly, let me check online. Are there any questions? Okay, while we wait, if there are any questions here, any further questions from?
Power changes. Is that what happens for general groups? For other groups, for SOs and so on?
Okay, so for other groups,
this M into M plus 1 will change, or?
So it looks like this. So IN is also still half big here, is 1 over Q square infinity without the 2. This is for SPK and N, okay, or SO 2K plus 1.
So these two are S dual too.
These two are ones which are dual by Monton and Olive. And the other one is exactly the same times 1 plus Q to the K. So this is for SO2K. Okay. Without fluctuations. So there's one, so the interpretation is that you can either have the usual giants or this, what I call the topological giant. And these ones have the usual fluctuations, but with Q goes to Q square. That's because in the orientifold, you have always 2 branes at a time. Or you can either have this brane or not have this brane.
Okay, so is there some analog to, like when you don't have like a large rank, like when you have exceptional groups and so on? Is there like a analogous question of what? Or we should think
Yeah, I
about
don't
these
even
things?
know. I don't know if anyone has done it. We can look up the, I know where to look, but I don't know the answer. Even whether the index is, it's been computed. Maybe someone.
Sameer, in your formula, should it be q power 2mn?
It's q here?
Yeah, the last term.
Thank you, thank you. This everything is q goes to q square. Thanks, Suresh.
Sorry, Sameer, Raghu here. Can I ask something? I missed the details of your explanation of this minus sign.
Sorry, can you say again?
In the first giant, there's an overall minus sign, right?
So sorry, can you start again, please?
In the G1, there's an overall minus sign, right?
Yes.
And earlier there were some explanations of that minus sign saying that this maximal giant has two unstable directions. So there are two eyes and there's a minus sign there.
Yeah, so yeah, go on.
Is your explanation related to that one, or are you giving a different explanation?
Yeah, it's kind of related. So I explained it as a -1 to the f. But you see, when B is positive, then the fluctuations reduce the R charge, so you have a series in Q inverse, which is not convergent. That's the sign of the, you can call it instability if you want. But because we are adding a QV action, we can control both of them. You can, depending on the sign of B or depending on the range of Q, you can either be inside the unit circle or outside, inside the unit disk or outside. The QV deformation that, I didn't spell it out, but I said in words what it is always positive definite. So I can control both sides and show the wall crossing. And the minus sign in this way of thinking about it comes from the -1 to the f fermion. So it's related, but I think it goes slightly beyond that.
Mm-hmm. Also, maybe just
We're talking about this paper of Ji-Hoon Lee, is that right?
And who?
What paper were you referring to when you said earlier? It
Yeah,
was
like Ji-Hoon single author paper.
Yeah, exactly. Yeah.
And there were some confusions in that, and just today, Ji-Hoon and Douglas Stanford had another paper.
Oh, I didn't see that paper. Okay.
That also talks about some imaginary phase space and bulk thimbles.
I should look at it. Yeah, we had conversations about it. I didn't realize that they've put it out. Okay. Yeah.
Yeah, that paper just came out today.
Okay, thanks. Yeah.
Okay, thanks.
Question I have is, when we were discussing the spectrum of fluctuations,
we
only discussed the giant, and then you showed that only maximal giants contribute. So what happens to the dual giants? They don't contribute at all?
Not in this way of thinking. So the overall integral is over everything, but when you localize it, it only goes to the maximal giants. It's as if everything else is canceling in this QV action.
So I had a question which is probably addressed to you and Raghu in some ways, because you mentioned about the general unitary integral. So like if you just not consider the index, but just consider the full free angles partition function, and then do this sort of expansion. Is it suggestive of a similar?
Yes, I think so. So in my first paper, I had the formula I worked out was for arbitrary unitary matrix integral. In fact, you could have an infinite number of couplings. And then Raghu is there, so maybe you can answer. You can then massage it. I don't know how much they used the index in their paper. Maybe you should answer.
No, it was completely general at the level of your first paper.
So, but my question is that it probably is not as simple as something like this, meaning the series. But how explicitly is it known, like the M for the mth giant?
There's a formula.
It's a reasonably explicit formula. And
so in my paper, I had an explicit formula, but I think the paper of Raghu and friends makes it more beautiful.
Okay.
Yeah, the mth giant is given as a 2m dimensional contour integral.
Very nice.
2m dimensional?
Contour integral.
2m dimensional contour integral.
It's
2m, little m.
Little m, the same as the number of gravitons, right?
Yeah.
Okay. Okay, good. So it's possible. I mean, there's some things, I mean, I was wondering how much relies on the magic of localization. I mean, probably to get the explicit answers, of course, but some of these things about this decoupling between the closed strings, open strings, and how much of it is, now, of course, now the partition function would also, in general, depend on the lambda. You can start at the free Yang-Mills, but then deform it away from it. And so I was wondering whether so now probably it's all the giants will contribute, probably all the dual giants and so on, and it's maybe that, so, but the answer doesn't immediately suggest something obvious, is it?
No, I think the answer is suggestive of some bulk. This 2M thing Raghu said, I think is suggestive of some kind of 2 stacks of M branes or something like that.
I see.
In the bulk. Is that a fair comment, Raghu?
I'm not sure about the bulk AdS side, as in like the eigenvalue instantons we had were on the matrix integral.
Yeah.
So I don't want to fully commit to a bulk interpretation. Especially at some level, it seems like these branes are in the infinite N theory. It's like, as you say, they're weakly coupled, right? So you're sort of taking the infinite answer, somehow putting the branes in the infinite N theory with these overall powers q to the that depends on capital N.
Absolutely, yeah. So this is something with all the localization calculations of going this way.
But that's fair in a sense. I think it's a kind of an expansion around that.
N equals infinity,
around large N. So that's probably fine. But my main, this thing is about the lambda dependence, and especially where this open closed versus how much anyway.
I mean, generally I wouldn't expect the fluctuation determinant to stop at the quadratic order, for instance, if it's, I mean, that will have a lambda dependence.
Right.
Meaning, as topological sectors, you can probably sum over branes. Let's say weak coupling. And then there'll be some fluctuations, but there's no reason why that, I mean.
I would actually like to say something stronger at some point, but I don't know, I don't have very, which is that the closed string background itself is made by these N branes, but then you need N of them.
Then you need N of them, but
that it's a deformation of from zero coupling by adding N branes. So at some level, but I don't know whether this expansion will
allow
that
for that
in a simple way, but that's a separate question. Okay. Any other questions online or here? Okay, if not, let's thank Sameer again.
Thank you.
Thanks, Sameer, for the nice talk.
Thanks, Raghu. Yeah, let's try to catch up. I had some questions for you, but maybe,
okay.
Yeah.
Okay,
Thanks.